This image is of crabapple or cherry petals floating in a pond. Notice how most of them have clumped together in certain areas, but a few have drifted off quite a distance from where the bulk of the petals are. These petals represent data points. In most sets of data, the values clump together and are close, but there always are a few that stray out from the rest, sometimes quite far, and we call those outliers, sometimes just a moderate distance. But all the data is not clumped together. That is the purpose of standard deviation. The standard deviation of a set of values gives an average of how spread out the data values are. Let us look at a small set of data. Here we have prices for wireless headphones in US dollars from a store. Since these are all of the prices for wireless headphones from this one store, we will treat the set of data as a population and not as a sample. The standard deviation measures the average amount that your full set of data differs from the mean. The mean is the average, or the sum of all of the values divided by the number of values that were in the set. We have 18 prices, ranging from a low of $27 to a high of $350. If we add all 18 prices, we get a total sum of $2,588. If we divide that by the number of prices, which was 18 prices, we get an average or a mean of $143.78. Notice none of the prices are actually $143.78, so all of the data differs from the mean. The question would be, how much on average do the values differ from the mean? Some of the values, like $133, are somewhat close to $143.78, but others are much farther apart, like the $27 or the $350. Again, the standard deviation is an effort at measuring the average amount that the values differ from the mean. We are going to average the differences from the mean. We need to find the differences from the mean. So let's start there. The mean again was $143.78. So we're going to find the difference, the subtraction between each of our prices and the mean of $143.78. So going down the list of 18 values, we found all of those differences. Notice some are negative, like negative $116.78 and negative $113.78. And then they start to become positive with $32.22 and then $82.22. And the highest difference is $206.22. And you find an average, what do? You add all of the values and divide by however many you have. So it seems like we should then add these differences and then divide by 18. But we run into a problem. If you added all of these differences, you would get a sum of 0. And if you divide 0 by 18, it's still 0. So we would be saying that the average amount that the data differs from the mean is 0, which would not be informative. In fact, every single set of data would report that same thing if that was the way that we decided to find standard deviation. If you find the mean of any set of data and you find all the differences of the values from the mean and you don't round, again, if you actually add these differences, you might not get exactly 0 because we rounded the $143.78. But if you don't round and you add all the differences, you always are going to get 0. The amount of negative in the sum cancels out the amount of positive in the sum, and you always get 0. So every set of data that was ever collected would have a standard deviation of 0. And again, that would not be informative. That would only be informative if we had a set of data in which every single value was what the mean was. So if you collected data and every single value was exactly the same, then that would make sense for the standard deviation. But most sets of data, that is not the case. So we need to find another solution for a measure that would give us the average amount that the values differ from the mean. We are going to use these differences, but we're just not going to do the traditional mean or average by adding them, because we would always get 0. I could understand if some of you are thinking, well, we just care how far the values are from the mean, so why don't we just ignore the negatives and just, delete them and average the actual absolute value of the differences and divide by 18. I mean, that certainly is a reasonable idea. There is a calculus reason why we're not going to go with that approach. And because this is an introductory statistics course, I'm not going to delve into the calculus reason, but there is a good reason in the big picture of what people end up doing with standard deviation. Instead, we're going to get rid of the negatives by squaring all of the differences, because a negative times a negative is a positive times a positive is a positive. So by squaring the values, we will not have negatives, and thus when we add, we will not get 0. So first we need to square all of the differences. So negative 116.78 squared turns out to be 13,637.5684, and negative 113.78 squared turns out to be 12,945.8884, etc. And then our largest value was 206.22. When we square that, we get 42,526.6884. So now we have these non-negative values. We are going to average them. Okay, so we're going to find the average of the squared differences, or squared deviation. The word deviation and difference mean the same thing in our class. When we add all of these squares, we get a fairly large sum of 192,719.111. Averaging these squared differences, we're going to take that sum and divide by 18, because that's how many values we have, and we get an average squared difference of 10,706.61728. Again, what is that? It's the average of the squared deviations from the mean. What will be more informative, though, if we were actually representing our data a little bit better. So we're not going to cancel the squares. We're going to dampen the effect of the squares by taking the square root of that average. So if we take the square root of the 10,706.61728, we get a standard deviation of $103.47. So this is a good measure of how much the different prices differed from the mean of $143.78 that we had gotten earlier. Here we have a number line showing all of our 18 prices and the mean. So we can see the mean labeled $143.78, and then the dots are the various prices that were in our set of data. Remember, we did have 2 that were $350, but the 2 are plotted on top of each other. So notice there are a few that are pretty close to the mean, but otherwise the data is, scattered pretty far up and down the number line. How much a set of data is scattered about its mean is measured by the standard deviation, but another way to get a gauge of how spread out your data is to find a value called the coefficient of variation. And the coefficient of variation takes the standard deviation, compares it to the mean, and turns that ratio into a percentage. So if we compare the standard deviation of $103.47 to the mean of $143.78, we get 72%. So the standard deviation is 72% of the size of the average data. That means this data is fairly widely spread out. The prices are relatively widely spread out, from a very low of $27 to a very high of $350. Like, somebody's going to notice spending $27 versus $350. If your coefficient of variation is above 50%, that's indicating that you have a set of data that is fairly widely spread out. More often than not, we will actually have a set of data that is a random sample from a larger population. Since our estimate of the population mean will be the mean from our sample, the sample values are likely closer overall to the sample mean than they are to the population mean. That's because not all extreme values would generally be in the sample, and this would drag the sample mean closer to the center than to the true population mean. To compensate for that, we will find the average of the squared deviations by dividing by n minus 1 rather than n. So when we have a set of data that's a sample and we're finding that average of the squared deviations, we're not going to divide by n, we're going to divide by 1 less than the number of data values we have in our sample. When samples are smaller, this alteration makes a greater alteration in the estimate of the average deviation. And when samples are large, dividing by n minus 1 does not make that much of a difference. With larger samples, you also are going to have more information about the population anyway. And so, your data is, going to tend to possibly be closer to the mean. To make the point that I'm trying to explain, suppose we had our 18 prices and they were a sample from a larger population, and we're going to make our population just a little bit larger. So suppose the store also had some headphones that were $378, $389, $400, and then a pair that was $25 and a pair that was $26. And our 18 prices are our random sample out of this bigger population. The mean of this larger set of data that includes the 400 and the 378 and the 25, etc., is $171.82. Notice the mean of this larger set of data happens to be higher than the mean of our original set of data. I mean, not that the population mean is always going to be larger than your sample mean. For this case, it was because we had 3 higher prices than we had extreme lower prices. But our data in our original set of 18 is going to be closer to the 143.78 than it is going to be to the 171.82. So this is making the point that any sample is going to tend to congregate closer to its sample mean than to the larger population that we're actually trying to talk about. Continuing to make the point with our example here, we are imagining that we have a slightly larger population of prices of wireless headphones that go from a low of $25 to a high of $400. The mean of that full population is $171.82. We took a sample of 18 of these prices. If we follow the process of finding the standard deviation of the 18 values that we picked and how they differ from the true population mean of 171.82, we end up getting $107.20 as a standard deviation of the 18 values from the true population mean. So notice $107.20 is higher than what we got when we looked at the 18 values as their own little entity. We ended up with a standard deviation of $103.47. So when you take a sample from a larger population, probably those sample values are going to differ by more than what you would get if you followed the strict definition of standard deviation and divided by n. So to compensate, if you want to make the standard deviation a little bit bigger, notice $107.20 was a little bit bigger than $103. So divide by 17 instead of 18, that is, divide by one less than your sample size when you're averaging the squared deviations. And for our example, when we do that, we end up getting 11,336.4189 as the average squared deviation. When you take the square root to dampen the effect of squaring, you get a standard deviation value of $106.47, which is closer to $107.20 than it was to $103.47. So again, in reality, you are not going to know the full population. You are going to have taken a sample. But this example is showing that when you take a sample, in order to get a better read of the true standard deviation from the population, you want to err on the side of making it a little bit bigger by dividing by n minus 1 rather than n. Again, in reality, you're not going to actually know the true mean of the population most of the time, or the true standard deviation of the population most of the time. You're taking a sample to best represent your population. But if you take your sample values and you follow the standard deviation process, find the deviations, square them, average the squared deviations, take the square root, you're going to end up with a value that's a little bit too small if you're really trying to represent how do the values differ from the true population mean. So to compensate, we divide by n minus 1, and dividing by something slightly smaller makes the standard deviation slightly bigger. There is a little more background to why we use n minus 1 and not some other just smaller number. It has to do with something called degrees of freedom. That is, if you knew the mean and you knew all the data but one, you could figure out what that one missing data value is. But again, that's beyond the scope of an introductory stats class. So for starters, let's just try to understand that if you have a sample, you're going to get a better read for the average deviation from the true population mean by dividing by n minus 1, making the value for the standard deviation slightly bigger. When you're working on finding standard deviation, I would recommend organizing your work as shown. We have a column for the data, and then we have a column for the deviations, that is the subtractions of the data minus the mean. We're not going to average those because if we did, we'd always get 0. So we square the deviations, thus creating a list of positive values. We're going to average the squared deviations, so add them all up. So notice we have the sum of the squared deviations at the bottom of that column. I'm going back to assuming that this was all the prices from one store, so we're treating it as a population again and not a sample. So I divide that sum by 18, giving me the average of the squared deviations. But if you take the square root, it dampens the effect of having squared everything, and that gives us a good read for how much the prices differed from the mean. So once again, we have $103.47 when we treat this as if we had the full population of prices. Now, in reality, you're going to have probably software do all this work for you. Excel has a program that will calculate population or sample standard deviation depending on which program you pick. Graphing calculators also give you both the population and sample standard deviation. But as an educated person, you want to understand what goes into values that you get from software. Similarly, if you follow sports, you're better off understanding what really goes into some of the analytics that the sportcasters talk about. Like in baseball, there's OPS, so you're better off understanding what OPS stands for, like what really goes into on base plus slugging. If you follow tennis, you're better off understanding what all goes into the rankings. If you're taking a class, you're better off understanding what your grade is by knowing what goes into your grade. So again, that's the point of us understanding what a standard deviation actually is. Like I, for example, know how to find a standard deviation. If I was given a set of data, I can do it by hand. If I need to, I usually use software to do it for me quickly, but I have an understanding of what it's actually measuring because I know the process. So that you could gain a deep understanding of the process, here is some practice. I would pause the video at this point and work with this really small set of data. Why don't you first assume that it is a population set of data? It's 7 values of calories burned during a day. So it's like 1 week worth of calorie data. So you could treat that week as its own little population and work through the steps to find the standard deviation, assuming it's a population, and then also find the coefficient of variation. Well, hopefully, as you work through the steps and got yourself a little snack maybe, you ended up with the same results as we have here. Again, I provided the table, but you should understand, why do we have these columns and what's supposed to go in the columns. So we have the column of data, and then you should have found all the differences or the deviations of the values from the mean. So you had to find the mean of the data. I didn't give that to you. So if you added the 7 amounts of calories and divided by 7, you should have gotten 2,452.57. And you find all the deviations. Again, you're not going to average those because you would end up getting 0 or something really, really close to 0. Instead, square the deviations, and the numbers are fairly big, so the squares are fairly big. We're going to average those square deviations. So if you added them all up, you should have gotten 891,341.7143. And divide by 7. Again, we're averaging the 7 square deviations. We're treating this like population data. So the average of the square deviations is 127,334.5306. But take the square root to dampen the effect of having squared, and we get a standard deviation of 356.84 calories. So notice our calories were all in the thousands and, close to 2,000, and our standard deviation is only 300 and something. So when we find our coefficient of variation, we only get 14.55%. So this set of data is much less varied than our previous set of data. Our coefficient of variation for the previous data was 72%. That data was much more widely spread out. A price of $27 was quite different than a price of $350. Whereas here, 1,950 calories is not as dramatically different from 3,000. So again, this set of data is fairly tightly compact. If you made a histogram of it, the bars would, look more tight together, whereas the other set of data, if you made a histogram, they look more spread out. To review the idea of the difference between a sample standard deviation and a population standard deviation, suppose instead of a week's worth of data, these were just 7 values randomly chosen out of a month or a year. And so we're going to treat it as a sample. We still go through the same steps. We get the same differences. We square the differences. We get the same sum, but we're going to divide by 6 instead of 7. And when we do, we get a sum, an average of 148,556.9524, which is slightly higher than what we had before. When we take the square root, we get 385.43 calories. So looking at it as a sample instead of a population, our standard deviation is slightly higher, If you compare that with the mean and get a coefficient of variation, notice it's now 15.72%, a little bit higher than 14.55%. So again, with data that you're viewing as a sample from a larger population, you build in a little extra wiggle room and make your standard deviation larger by dividing by n minus 1 instead of n. In any set of data, most of the values are going to be packed closely together, just like these petals, but some are scattered further away. The standard deviation of a set of data gives an average amount of how spread out the data values are from each other, but specifically how spread out they are from the